By the way, you forgot to record.
Tamam, biriniz record edebilir mi? Veya ben şuradan record edeyim.
Okay, Enis started the recording.
Okay. We can divide as with our previous analysis, we can divide it into two parts. One is the one that we do, and the other is the recursion part. I mean, we can analyze it as if it's recursively. Let me write that first. We can divide the complete analysis into two parts to make it easier. So here in the pseudocode, the basic operations, okay, what are the basic operations? The basic operations are these two comparisons, right? Let me write that first, basic operations. Okay, and T1 is the first comparison, and T2 is the second comparison. Okay, so expected value of T1 is n-1 because independent of the data and its distribution, I always make this comparison because it's in each iteration of the for loop, right? I execute this if statement in each first step of each iteration of the for loop. So that's why it is executed as many times as this for loop iterates, which is n-1, okay? Because it's 2 to n. So expected value of T1 is equals n-1 independent of the data and its distribution. Okay. For the second one, it depends on how many times the first comparison is evaluated, okay? Because I don't need to execute it in each iteration. If the first condition is true, then I don't execute this inside the second if, okay? So its expectation is, and T1 and T2 are independent of each other, okay? Let me write that. Depends on how many times the first comparison evaluates to true. So this is random. This is what makes it random because the first one is deterministic. We take the expectation, but it's always n-1 anyway. So obviously the expected value is exactly equal to n-1 in each case. But the second one, it depends on the output of the first comparison, how many is evaluated. So, and it's actually equal to n-1. N-1 comparisons are made for the first comparison, minus x, big X, which is a random variable denoting how many times the first comparison has evaluated to true? Okay, because if the first comparison is true, I don't execute it. So I subtract it from n minus 1. Okay, I execute it only if the first comparison's result is false. So this is n minus 1 minus x, but here n minus 1 is deterministic, of course, I know n, but the big X is a random variable, so it's probabilistically. We don't know the result of the first comparison. So overall, I can say that this is equal to 2n minus 2 minus expected value of x, right? So I will find the whole average case once I calculate the expected value of x. The first comparison is true. Let me introduce another random variable. Let y be a random variable. Sometimes I denote it as like this, random variable. Such that y is equal to I means that ln is equal to I. So the list has, the value there is I, okay? In a particular index is I, then it's a random variable, okay? So the expected value of x is that expected value that the first comparison evaluates to true, okay? Expected value of x is summation for all indices 1 to n. Expected value of x given that the index is the value of the list in that particular index is equal to I, okay, times probability that it is actually equal to I, okay? So this is conditional expectation as we did previously. Here we partition according to the value of the last element in the list. So in quicksort, we partitioned according to the pivot element, okay? So this is like expected value of x given that the ln is equal to I, let's say, okay? So suppose that the last element is the largest element. So it's like 2, 3 example, let's say 1, 4, 5. So the first comparison will be true for 3 times, right here. So what does the first comparison? The first comparison checks whether it's greater than the max value, okay? Li is greater than the max value. So I will go on to the to the end of the list always. I go on from I to n, 2 to n. Here I will start with the 2 and then I will say, okay, is it greater? 3 is greater than 2? Yes. Okay. So the first comparison will evaluate to true here. Okay. In what's okay, the first comparison here. Is Li greater than max value because max value was 2 first? Yes, it's greater. But then is it greater? No, 1, because now my max value is 3. But then 4 will be greater, so 2 times it evaluates to true, and then 5 will be greater, so 3 times it evaluates to true, for instance, in this case. Okay, so in 2, 3, 4, for instance, 2, 3, 1, 4, for instance, I have it like 3 is now my max. Okay, 2 was my current max value. 3 is greater than 2, which is true. 1 is not, but 4 is, so it will evaluate to true 2 times. Okay, so 2 times, twice. So if y equals n, okay, if the largest is then dn is actually dn minus 1 plus 1, right? Because it's, if the maximum element is the largest element, then what's equal to? I will find the maximum element in the list, indexed in the sublist, indexed from 1 to n minus 1. That's what I'm actually doing. Once I start from the first one to towards the end. So once I arrived at the part of the list with index n minus 1, what have I done actually? I have actually found the maximum in this portion, right? In this portion. And then I mean, in his case, I found the maximum in this portion, okay? So finding the maximum if dn is my average case, for instance, or the number of comparisons, let's say, dn. So the number of comparisons here is dn minus 1. I'm actually doing the same thing for a list with size 1 less than that. But if my maximum is the last element, then the number of times, then in the last iteration of the for loop also, the if statement will evaluate to true because it's bigger than the entire thing. Okay, so if my last element is the biggest element, so I can express it as a recursion, because this one comes from the last comparison. The last comparison will also evaluate to true. So I have dn minus 1 comparisons first, plus I have another comparison which is 1. So dn becomes dn minus 1 plus 1. This is for one possible case where the largest element is the last element. Okay, but what about the other cases where it's not the case? Because if it's not the case, then for the final case is dn is equal to dn minus 1, right? But if it's the second largest, third largest, etc. Okay, sorry. For other values of I, n minus 1, then because it doesn't evaluate to true, dn is equal to dn minus 1 for other values, for all other values, if the last one is not the largest element. Okay, if the last element is not the largest element. So I can break it into two cases, okay, the analysis. If the last one is the largest element, I have one recursion. And if it's not, then I can express it as now, because the last one will not evaluate to true. Okay, if it's not the biggest, then I won't have an additional case. So I can write it as this then, dn, number of comparisons, expected value, a summation I from 1 to n minus 1 dn minus 1 times 1 over n. Okay, for 1 to n minus 1, it's not okay, because in that case, for 1 to I, y, remember that y is a random variable saying is equal to I. Okay, if it's 1 or n minus 1, then dn is equal to dn minus 1. If y is equal to n, then dn is equal to dn plus 1. So for 1 to n minus 1, I have this recursion, plus for the last case, I have this one, dn minus 1, dn minus 1 plus 1 times 1 over n. Okay, 1 over n also means that it happens with equal probability. So this n does not depend. So none of these depend on I, dn minus 1 times 1 over n. So dn minus 1 over n will go outside the summation times summation 1 to n minus 1, 1 means it's n minus 1, okay? So this part is actually n minus 1 over n times n minus 1, okay? I sum this term n minus 1 times, basically. So plus 1 over n times dn minus 1 plus 1 over n, okay? I'm just opened up the summation. So this is equal to what? This is equal to dn minus 1. Okay, this is what? N minus 1 over n here. 1 over n here, which makes what? N over n, which is 1. So that makes dn minus 1 actually. Plus 1 over n term here. Okay? So dn, so what I have is dn is indeed dn minus 1 plus 1 over n, and d1 is 0. Okay? So d1 is 0. d1 is 0. d2 is d1 plus 1 over 2. Okay? So d3 is d2 plus 1 over 3, which makes what? d1 plus 1 over 2 plus 1 over 3. Okay, right? So once by backward substitution, I find that this is actually dn is equal to what? d1 is 0 anyway. So it will be basically hn minus 1. This is like 1 plus 1 over 2 plus 1 over 3. This is the harmonic series. Harmonic series, okay? dn is hn over 2 minus 1. So expected value of x is equal to dn. That's what we said, okay? Yes. Harmonic series. So expected value of n is equal to 2n minus 2 minus expected value of x. So that means 2n minus 2 minus hn plus 1. Okay. I replaced it. I had already found this 2n minus 2 minus x, how many times the first condition evaluates to true, that expectation. So that becomes 2n minus hn minus 1 expected value of n. Because this is a minus term, it doesn't matter. So it's indeed theta n. Okay? But the exact value is 2n minus hn minus 1. So in fact, this is the lower bound for this problem. So no algorithm can achieve better than this, because I already scanned the list. So obviously the lower bound is also this. So it's theta. Okay. So this is the precise analysis of why this is linear. It may seem obvious at first that it's linear because I do a single scan anyway, but I do a single scan, but it could be more than that also. If in some parts of the iteration I was doing more than a constant number of operations, then it could be more, but we have shown that this is not the case. It's indeed linear time. Okay, And that comes in the minus term over there. Gelmedi mi? Ekran. Evet. Düzelteyim. Toplantıya döndük ama tamam, tekrar başlayalım. Okay, so this is the analysis. I will not do fast matrix multiplication, which is also interested, but let's overview now graph search and traversal algorithms, depth first search and breadth first search, because there we don't have numbers. Okay, we have a graph, an object actually. It could be some other object also. So graph search and traversal algorithms. So here I'm given a graph, for example, this, it could be something else too, but. Okay, let's say that this is my start node. How do I search, traverse all the graph? So what does traversing the graph means? Traversing a graph means visiting every node and vertex, okay? You might visit it more than one time sometimes, but optimally, ideally, you wouldn't want to do that. So if this is a network, for instance, and if you have a message that you want to send it to everywhere, but not only to every node, but also you want to pass through every edge. Okay, so that's what graph traversal means. There are two basic graph traversal algorithms that I think you already know of. One of them is depth first search, and the other is breadth first search. Okay. Does anybody remember what depth first search is? And if yes, can you please explain it? Okay, here, for instance, if let's say that my start node is node 7. Mikrofon kapalı sandım da. Okay. From the online class also? What is depth first search?
Ma'am, was it something
Yes.
along the lines of this? We go until the end of the list and search going back?
What do you mean until the end of the list? For example, I start with 7. Then how do I proceed, for instance, with depth first search? 7. Now what do I do?
Do we go 219?
No. I'm not asking 219. I'm just saying that what's the next step? You say 2, okay? From 7, you go to 2, okay? Then from 2, then where do you go? You say that you go to 1, right?
Yes.
But you could also go to 3. It wouldn't matter, right? So what you do is actually in the first step, you pick, if 7 is my start node, you pick one of the neighbors, right? You could have picked 2, 8, or 4, because it has 3 neighbors. Okay, 7 has 3 neighbors, 2, 4, or 8. And you decided to pick 2, right? Because it wouldn't matter anyway. But now you proceed with one of the neighbors, one of the unvisited neighbors of 2 now, right? But you don't want to visit another neighbor of 7. Like you don't go from 4 to 8, but you go deeper. It means that you could go to 3 because that's not a neighbor of 7, or you could go to 1 and you picked 1, right? Your friend, because he said 7, 2, 1. That's why I'm saying 7, 2, 1, because it wouldn't matter. It could be 7, 2, 3, but it's like that. Okay, 7, 2, 1, and then you say from 1 I don't go to 8. That's already a neighbor. I want to go deeper, so I go to 9, and then from 9 you go 6 maybe. Okay, and then from there you go 5, but then you come to 4, which is a neighbor of 7, and you don't have any other option. Now you do some back step. Okay, you roll back now. You roll back to the point where there is another neighbor that you haven't visited, and you go deeper down the list until you reach a point where you have to take one of the neighbors of the original. Okay, and then you go back one step. That was called, I don't know, piggybacking, no, something like that. And then you go on that way. So that's depth first search, right? So if I were implementing breadth first search, then how would I proceed? I start with 7, and then I do what? With breadth first search, do you remember? Yes. Okay, so I visit 2, but then I don't continue with 1 or 3 in that direction. I visit all neighbors of 7. So I simply, after 2, I visit 4, from 7 to 4, and then 8. So I sweep like across all the neighbors. And then because I started with 2, I pick 2 first, then I visit all the neighbors of 2 and be done with it. So I will visit 3 and 1, but then I will visit all the neighbors of 4 also, because I started with 2, 4, 3. All the neighbors of 4 or 5 and 6, and then 8, 1 is already visited by 2 now, so I just visit 8 and I don't visit anything else. So I go on in this manner recursively in each step. I don't exclude any unvisited neighbor. I visit all the neighbors. I don't pick a neighbor and go deeper down in that level of the tree, but I continue sweeping across all the neighbors once I'm done with all the vertices and edges. So that's breadth first search. Okay. So one question to you. So actually I could have, for instance, this is not a tree. This a graph. A tree is a connected and a cyclic graph. A connected graph, and that does not have cycles. It's the official definition of a tree. Because this graph has cycles, many cycles actually, the graph is not a tree, but the way I visit can be represented by a tree, and this is called the DFS tree, for instance. Because I start with 7, I can treat it conceptually as like the root of a tree. So, and then I go with 2, and then I go with 1, and then it has like 3 and 8 as neighbors, but I don't go with 8 because it's a neighbor of 7 in the original. I go deeper. I go 4, 5, 6, 9, etc. And then once there is a loop here and I don't have any option, then I go back there, and then I continue going deep down from that direction. Okay, this is called the DFS tree. DFS tree. But with breadth first search, you don't go deep down. You go like you picked you do 7, 2, 4, 8, and then with 2 you visit all the neighbors, 1 and 3, not 4. You've already done that. With 4 also you visit all the neighbors, 3 you've already done that. So all the neighbors that are not visited yet. So it will be like 5, 6, etc. So it will have, and that's why this is called depth first search, because you go deep and in the depth direction. But now in the breadth first search, it's like you're more in the breadth direction. Okay. So now a question for you to think. Imagine that okay, let's make it simpler, that your graph is a tree itself, okay? Your graph is a tree, but it's an infinite tree, infinite, okay? Conceptually. And you want to guarantee that you travel this, you're searching something, okay? It's called breadth first search. So you will keep on traversing it until you find something that you're already that you want to find. For example, each node can have an integer associated with it here, and I may be searching for a particular integer, or it could be colors, or it could be anything, okay? So you're searching something. Your graph is a tree itself, but it's infinite. And you want to guarantee that you will find what you are looking for in a finite amount of time, even though your graph is an infinite tree. Okay, so it's an infinite tree. Your input graph is an infinite tree, something like this, but it's infinite. Okay, you don't know where it ends. It never ends. You're searching for something, but you want to guarantee that, you want to ensure that you find it in a finite amount of time. Which algorithm would you prefer? Depth first search or breadth first search? Why? Might go to infinity if it's on an infinite branch. Not all the branches have to be infinite. It may be finite in some of them, but one of them might be infinite. Okay. But with breadth first search, so we know why it doesn't work. That's an explanation for why it doesn't work for depth first search, because you go deeper down it. If it's an infinite branch, then you die. Maybe it was on some other branch, but you will never be able to reach it. Okay. But with breadth first search, then why does it work? Less element than that? Or, but you don't know, maybe with depth first search you were lucky and you found it immediately, and with breadth first search maybe you made even more comparisons. Why does it work with breadth first search? So your answer is half true. You explained, your answer is true, but your explanation is half true. You explained why it doesn't work for depth first search, but it's not yet an explanation for why it works with breadth first search. Even though it's an infinite tree, why can you guarantee with breadth first search that you will end up finding what you're looking for in a finite amount of time? Finite. Finite doesn't mean a small number, but finite. So you will definitely find it. You will not wait for eternity. Because of the nature, I'm explaining it because we have 2 minutes. Otherwise, I would wait for you to think more. But because of the very nature of the algorithm, you scan all the neighbors, okay? And then you go you pick one of those neighbors and you scan all of these, but you don't go deep down there. You continue with the other neighbor and scan all of these. So at some point, you will definitely reach what you are looking for in a finite, because you go neighbor by neighbor and you don't exclude any branch. Even that branch might be infinity, but you don't get lost in the infinity. Instead, you scan the other neighbors and you will find it at some point. You will not die in infinity, okay? Because those branches might lead to somewhere in like infinity, but you will find it. It's like, for instance, it's usually in theoretical computer science, but for instance, if you have an infinite tape, let's say, going infinite in both directions. So it's like you are in a room and, okay, it may go on because I'm explaining anyway. And maybe your eyes are blind or you just look at a black wall, okay? Or, but you know that at some point on the left or on the right, what you're looking for is there. But it's infinite. So you can't go like in one direction, okay, I couldn't find it here, let me go into that direction, kind of thing. Okay, this is called the Turing machine tape. And the way to guarantee it, that you find what you're looking, you can only see where you're looking at. You cannot look at the other directions, okay? So you can go here, for example, look at what it's there, and then come back to your original point. Go here, 1 unit, look at whether what you're looking for is there or not. Think of it like a robot that can see only what it's looking at, okay? And then again come to the original, but this time
Your screen is off.
and look. I know, because I'm explaining it in class. Sorry for the online class. I don't have a camera here. I'm performing a theater performance, okay? I know. And then you go to the 2 units from the original direction to the 2, and then this will guarantee that you will find what you're looking for in a finite amount of time, even though your tape is infinite in both directions, okay? It's similar to breadth first search, actually, because you keep on sweeping, you don't leave out anybody, you are fair to all your neighbors, and you just go 1 unit, you advance your position. Again, you don't leave out anybody else, you are fair to everybody. So if you're fair, you will solve things. That's the result, okay? You don't put so much influence only in one direction, okay? Because it might not work and you don't want to get stuck. You need to try all the possibilities. And if it doesn't work, you go to the other possibility. But so that's the solution for not getting stuck up in infinity, okay? So see you next week. Your homework will be announced this week. I think your TA is not here today, but the second homework. So you will have it until your midterm. Your midterm is 2 weeks later, I think. So next week we will be starting our other book. If you want to look what we've done, we'll start exhaustive search and yeah, breadth first search. I explained the design of algorithms. Okay, the more interesting part of the course, at least more interesting for me. Bye bye.
See you.
See you.